All right, in this video, we're going to be talking about other features of rational functions that we are going to use to help us graph. In the previous video, you saw vertical and horizontal asymptotes. In today's video, we're going to be talking about holes, intercepts, and increasing and decreasing ranges. The first thing we're going to talk about is holes. And if we rewind a little bit, the word discontinuity is very key when we're talking about rational functions. Discontinuities are values where rational functions simply don't exist. This could look like an asymptote, as in a vertical asymptote, but it could also be seen as a hole, which is what we call a removable discontinuity. Okay? A hole exists on the graph of a rational function at any input value that causes both the numerator and the denominator of the function to be equal to 0. Essentially, what we're talking about here is if we had some function and it was fully factored, there is a factor that can be divided out from both the numerator and the denominator. Look at the example on the right here. I have an x plus 2 in both my numerator and my denominator. I could factor that out. I could divide this out. Okay? And because I'm able to do that, I can say, well, there's going to be a hole at x plus 2 is equal to 0. I took the factor that I divided out and I set it equal to 0. I could rearrange and say that there's going to be a hole at x equals to -2. And I've tried to include it on your graph here so that you can see this is literally what I mean when I say a hole. There is a hole in the function. We draw it as an empty circle, just like with number lines on the graph there. Now, in order to figure out the y-coordinate of the hole, all we need to do is we need to substitute in the x value of the hole into the simplified function. So in this case, our simplified function is x minus 1 over x minus 3. And we know that there is there's a hole at x is equal to -2, so I'm going to sub in -2. Which is going to be -1 over, sorry, I dropped a negative there. This should be a negative, -1. So this would be -3 over -5, or just 3 over 5. Okay, that is where our hole is going to be located at. And you would use that when you were sketching. You would immediately draw the hole on your graph before you sketched anything further. Okay, let's do 2 sample questions here. Determine if there are any holes and where they are located. So remember, you need to be working in fully factored form in order to determine where your holes are located. So I'm going to factor. My numerator is a simple trinomial with factors x minus 3, x plus 1, and my numerator is a difference of squares of factors x minus 1, x plus 1. Oh, and we can clearly see here we've got the same factor in the numerator and the denominator that we otherwise would be reducing. So there's going to be a hole at x plus 1 is equal to 0 or x is equal to -1. We figure out where that's located. F of -1 is equal to -1 minus 3 divided by -1 minus 1. That'll be -4 over -2, or just 2. So I have a hole at the point -1, +2. For my second function here, again, I need to be fully factoring it. Upstairs, I've got a complex trinomial, and the factored form would be 2x minus 1 times 2x plus 3. In my denominator, I have x minus 1. There is nothing that I can simplify out of both the numerator and the denominator. Therefore, there will be no holes. which I combined into one word. No holes. in this function. Not in that one. Okay, sometimes they exist, sometimes they don't exist. Okay, that one's pretty straightforward. Let's talk now about intercepts. Intercepts are something you've been working with for years now. You should be pretty comfortable with them. In order to determine your x-intercept, you need to set the whole function equal to 0. And in order to determine the y-intercept, you need to let x equal to 0. Okay, we are being asked to find the intercepts of the following. I'm going to start by finding the x-intercept by checking when f is equal to 0. Well, my numerator, 2 times 0 would just be 0, so I would have -5 upstairs. Actually, I'll show the substitution. No problem. 2 times 0 minus 5 divided by 0 squared plus 3 times 0 plus 2. That's a 0, that's a 0, that's a 0. I have -5 over 2 is my, this is my y-intercept because I set x equal to 0. My y-intercept. And we could actually write that as a point, 0, comma, -5 over 2. Okay, to do the x-intercept, we set the whole function equal to 0. And I would be taking my denominator timesing it out. So I'd have 0 times x squared plus 3x plus 2 is equal to 2x minus 5. And 0 times all of that is just 0. So I'll have 2x minus 5, rearrange here, and I'll have x is equal to 5 over 2. So my x-intercept here is 5 over 2, comma, 0. Okay, we can do the same thing for the next one. Let's find our y-intercept by setting the whole function equal to 0. By setting x is equal to 0. So I'll have 3 times 0 squared minus 5 times 0 minus 2, all divided by 0 squared minus 2 times 0 minus 8. That's 0, that's 0, that's 0, and that's 0. So I have -2 over -8, which is just 1 over 4. So my y-intercept is 0, comma, 1 over 4. And then to find my x-intercept, I set the whole function equal to 0. We saw what happened last time, right? When we multiply out the denominator, it just sort of disappears. I'm not going to show that step. We can just set the numerator equal to 0. And now I need to factor this in order to find the x-intercepts. This is a complex trinomial, and the factored form is 3x plus 1 times x minus 2. So I need to set both of these factors individually equal to 0. And I will have x is equal to -1 over 3 and positive 2 as my two x-intercepts. -1 over 3, comma 0, and 2, comma 0. Okay, cool. That one was pretty easy as well. Just setting things equal to 0 and solving. And the very last sort of feature that we're going to be talking about in this video is slopes. Slopes of our function. One of the ways that you can think about this is if you're going sledding, are you going uphill? Like this? Or are you going downhill? Okay, you could also think of it as increasing or decreasing. Think back to your grade 9 days when you were first introduced to y equals mx plus b. What was a positive slope? What was a negative slope? Slopes help us to graph the function. They're not 100% necessary, but they're a good way to sort of check your work. Okay. So let's take a look here and determine the intervals where the slope is positive and negative. Okay, so in our first graph, it looks like we are negative sort of on this side. It's going downhill. And on the right-hand side of the graph, it's going uphill. Where does the downhill bit stop? It sort of looks to me like that 0 is a bit of a turning point. And so we would say it is negative over here on the interval negative infinity to 0. And it is positive over here on the interval 0 to infinity. What about our second graph here? We've got a couple of different intervals. Definitely looks like this left-hand bit is positive, it's going up, and it also looks like there's some positive stuff happening over here. But there's a negative bit in the middle. It's a very steep negative, for sure. Yeah. Okay, so this one is going to be positive on the intervals where we start at negative infinity. And how do we know where is it going to sort of stop? It looks like maybe there is a vertical asymptote at -3. It might be at -2 for all we know, but just based on the graph, I'm going to say -3. And so I'm going to say this is positive on the interval negative infinity to -3. And then again on the interval 0 to positive infinity. It is negative on the interval, everything sort of between -3 and 0. Okay, and then the last one that we'll take a look at here, it's definitely negative on this first little bit here. It's coming down, and then it looks like we have a vertical asymptote at -2 that sort of stops things. And then it starts going positive again, and it does this little swoosh thing in the middle, but the swoosh thing remains going up. It doesn't ever come back down. So this is positive going this way. And then our last little bit is also positive, although it does look like we have another vertical asymptote located at 2, or at 1. Okay, so we'll say it is negative from negative infinity all the way through to -2. And it is positive between -2 and 1, and 1 and positive infinity. Okay, so let's pretend you've been given the equation instead of the graph, and so you got to figure out where it is going to be positive or negative. There are two things that we need to consider that are going to create these sort of intervals that we need to be testing on. Similar to how we found for our polynomial functions, we found some intervals. We do need to be checking for x-intercepts. That's going to inform our intervals. But the other thing that's going to inform them is the vertical asymptotes. That's what's going to be splitting up sort of our x-axis and how our function is behaving. And then we're going to be finding two numbers. We're going to pick two values in each interval and substituting them into the function in order to determine if the slope is positive or if it is negative. Okay, let me show you what I mean. We'll do an example together. So first things first, we need to find our vertical asymptote of our function f of x is equal to x minus 1 divided by x plus 3. Our vertical asymptote here is located at -3. Our x-intercept is located when y is equal to 0, or when f of x is equal to 0. And we saw above, we can just move quickly and jump right to the numerator being equal to 0. And so we know that x is equal to positive 1 for our x-intercept. That's the only x-intercept we have. So to help keep myself organized, I'm going to draw a number line here. Let's be better with our spacing. There we go. And there were two key values we were looking at. Again, we said our vertical asymptote was at -3, and our x-intercept was at +1. So we have three intervals that we need to be testing against. The first interval is going to be over here. The second interval is going to be this one in the middle. And then the third interval is going to be this one over here on the right-hand side. So we've got three intervals that we are testing on. We are looking between -∞, -3, between -3 and +1, and then everything from +1 all the way to +∞. Okay, so let's check our first interval between -∞ and -3. I need to pick two numbers within this interval that are sort of near enough to each other and that are going to be easy to substitute in. So I'm going to be checking against when x is equal to -5 and when x is equal to -4. If you think about it on a graph, I am moving from left to right between -5 and -4, and that's the goal. Okay, substitute these in. F of -5 will be -5 minus 1 divided by -5 plus 3, which is -6 over -2, or +3. F of -4 will be -4 minus 1 divided by -4 plus 3. -4 plus or minus 1 is -5. -4 plus 3 is -1. My answer is 5. I'm moving from left to right. From 3 to 5, I am increasing. And so I know that on this range, my function is positive. I am moving up. Okay, we do the same thing again, just on our second interval now, between -3 and +1. All right, two numbers going from left to right. Let's pick x is equal to -2 and x is equal to 0, because 0 is nice and easy. Substitute them in. F of -2 is -2 minus 1 divided by -2 plus 3. -2 minus 1 is -3. -2 plus 3 is +1, so I have -3. And then we check f of 0, so that'll be 0 minus 1 over 0 plus 3, which is just -1 over 3. I am once again increasing as I go from -3 to -1. Therefore, this interval is also positive. Right? I know I'm increasing. I'm going from a less negative number, or sorry, more negative number. This guy's further down in the negatives. This guy's closer to being positive. All right, and our last interval 3, is anywhere from +1 all the way off to infinity. So let's check against when x is equal to 2 and when x is equal to 3. Substitute them in. F of 2 is going to be 2 minus 1 divided by 2 plus 3. 2 minus 1 is 1. 2 plus 3 is 5, so I have 1 over 5. F of 3, so we'll have 3 minus 1 over 3 plus 3. 3 minus 1 is 2. 3 plus 3 is 6. So I have 1 over 3. Okay. 1 over 5, it's going to be increasing once again. My numbers are getting bigger, right? This is like 0.2 and this is 0.33. I'm increasing. So on my little interval chart here, I'm also going to be writing a little plus sign. If I wanted to write a therefore statement, and I'm going to write it back at the top here, I'm going to say therefore this function is increasing on the intervals -infinity to -3 and -3 to 1 and 1 to positive infinity. Okay? Last but not least, I'm just going to take a look and I'm going to see, well, I have here at 1, this was my x-intercept. My function actually touches this point. And so in fact, at 1, I should not have curved brackets, I should have square brackets. Because 1 is being included. My function is equal to 0, yes, and 0 is neither positive or negative. But I don't care what my function is equal to, what I care about is if it's increasing or if it's decreasing. And so because 1 is included for both of these, I can actually merge them together. These are going to be merged, and my final answer will be -infinity to -3 and -3 to positive infinity, because these two guys can be merged together. Okay? And that's it. So we've got a lot of good information now for sketching our rational functions. Today we talked about wholes, we talked about intercepts, and we talked about increasing and decreasing ranges, all of which are going to be pulled together in the next lesson when we actually graph. Great work, everybody.